We'll start with announcements, because there are a good few. This is an important week. We have a homework due tonight. We have a study session tomorrow, so this is the last day of new content before we dive into tomorrow study session and Friday exam. Because I haven't had a chance to look into this, have we gotten feedback on our first homework yet? Not ideal. Okay. I will keep that in mind with regards to what is to come. I know our grader got sick, and that doesn't help him, it doesn't help any of you. So it's something that I will keep in mind moving forward. I don't think I can change the pace of the course to make up for that, just given how full it is. But again, I'll carry forward knowing that this was an extra challenge, an extra unnecessary challenge that you all faced moving forward. Let's see. Anything else? I think that's basically it. I do have a little bit of limited time today due to house stuff. So I'll have my typical office hours, the hour after class, and I'll probably have an hour between 12 and 1. But at 1, I will probably have to be out signing a mountain of paperwork. And throwing my life savings away.
It's an investment.
It is. Yeah. Yeah. The non-liquid investment in a market that may completely and totally crash in the next year or two.
True.
All right, so we're in the middle of a pumping lemma, and last we checked in, this is a bit of a struggle, and understandably so, because it's quite challenging to wrap your mind around. And even when you do, there are going to be problems that are quite difficult within it. The first example problem that we showed was a string followed by that same string in reverse. We wanted to show that that is not regular using the pumping lemma. So we picked a W of A to the M, B to the M, so that WWR was A to the M, B to the M, B to the M, A to the M. And here's a visualizer of what that would look like, and a good bit of how and what we could do with regards to X and Y, because the rest of the string is Z, but we know that X and Y, by the definition of a DFA, have to occur within the first M characters. There has to be some loop. We're going to find the first closing of a cycle that we can get to. And if there are M states of the DFA, then we've derived a string based on that number of states. So we know that X and Y now have to consist of all A's, because there are as many A's in this string as there are states in the DFA, which means we're closing some cycle by the time that we're reading the A's. So X and Y, this concept of getting to that cycle and iterating that cycle for the first time, have to occur with all A's. And what that means is that we could iterate that cycle more than once. So there is some path from an initial state to a final state in this DFA that reads this A to the M, B to the M, B to the M, A to the M. The only thing we are saying is we've cut out this cycle Y, and now we repeat it. We take exactly the same path that we did through X and through Z, but we're going to repeat the cycle Y. And as we do this, we see that we are adding at least one A to the first part of the string, and we're not adding any A's at the end, because whatever path that we took before to accept this, we're going to take exactly that path, which is going to produce exactly this many A's at the end. But we're choosing to iterate this cycle Y one extra time. Adds at least one A to the string, and now we don't have a string in WWR. This is no longer an even length palindrome necessarily. How are we doing with that? Does that make sense? Or to what extent does the explanation logic of that make sense? Can anyone kind of walk through how you feel about this, or just kind of share the parts you feel like you understand, the parts you feel like are not clear?
Parts I feel like are kind of clear is the option of adding more.
Yeah. each cycle. Yeah.
For me, the thing that's unclear is the fact that player one picks M, and I'm confused. So like, if M is one, what do we do then?
So we're saying basically, if M is one, there's a one state DFA.
Okay.
Which means all we can do is have a self edge on that, and somehow that's going to accept all of WWR. That's okay. We're going to run with that assumption. But the string we pick is A, B, B, A. And the breakdown of X, Y now forces that Y to be that self edge. So that means that if that consumes that A, then we can take that twice and produce two A's. And then somehow within just that one state, we were able to produce BBA. So however we did that before, it's impossible by thinking of it as a one-state DFA. But however it is that we did it before, we're going to do it again. But now we produced AA, BBA by taking the cycle that had to have been there within that first character and repeated it. And I know that doesn't really make sense because you can't visualize a one-state DFA that solves this problem because it just makes no sense. There's no way you could possibly represent WWR in one state. But if player one says, I can do this in one state, your counter to that is what I just described. If they said there's a two-state DFA, then you're going to pick AA, BB, BB, AA, and you're going to go through exactly the same logic. If they pick a 27-state DFA, you can go through exactly the same logic.
So it's not always A's being, or is it always the A's being our Y?
It is always our A's being our Y, because we produce M of them, and player one gives us M, the number of states. So our string will always contain as many A's as they state there are states in the DFA. And since XY, the length of XY has to be less than or equal to M, because that has to close a cycle by that point, we know that we've reached a cycle somewhere within the reading of those A's. How are we doing with that? Does that help? Does that make sense? We have to close that cycle in the first M characters. Is that part clear? Solely looking at closing a cycle within the first M characters. Show of thumbs. How are we feeling about that? All right, I'm going to say we should draw that out again.
Yeah, and that's due to the condition, right? That XY has to be less than M. And
yeah, that's the condition that closes a cycle.
Okay. Yeah. So.
Yeah. So let's draw this at a bit larger DFA than 3 states, the way that I've been visualizing it before. Let's do it with, I don't know, let's do it with 5 states. So if we have a 5-state DFA, I kind of want this to be visible. A little bit more space than we have here. We'll have 1 state, 2 state, 3 state, 4 state, 5 state. So we have an initial state, and it doesn't really matter what our final states are. They could be any subset of this. But if we're reading WWR, that says that we're going to have some string followed by that string in reverse that is going to be accepted within these 5 states. In order to fail to create a cycle, because a cycle is something that can be repeated some number of times, you can imagine that without this Y, we just take XZ. That is a path from an initial state to a final state. That is some path that goes maybe here, then here, then here, then here. XZ is as long as we can get without some kind of cycle. But at some point, we have to close a cycle. What are the most characters that we can read without closing that cycle? It is this. You go from the initial state, visiting a state we haven't visited before. Visiting a state we haven't visited before. State we haven't visited before. State we haven't visited before. As soon as we go back to a state that we visited, we're closing a cycle. How many characters have we read? If this is an A, this is an A, this is a B, and I don't know, this is an A. Doesn't really matter, but how many characters have we read? The number of states minus 1. As soon as we read the number of state character, we have to have closed a cycle. It could have been that we closed a cycle before that. We could have a self edge on the initial state. That would close a cycle with the first character that was read. But by the time we read that fifth character, once we're at this position and read AABA, we have to go back to some state that we've seen before, closing a cycle when we read that fifth character. So if M is 5, then we're saying that by the time we read the fifth character, we have to have closed a cycle. Once we've closed a cycle, we can identify where is that cycle. So maybe we have a cycle right here. Maybe this is a B. By the time we read, this would be now X, reading this A, getting to the start of the cycle. Then Y would be reading this A, then B, then B. We could repeat that an arbitrary number of times and end up back where we were when we started the cycle in the first place. So we could, by saying that, let's say this is our accepting state. We could read the string A, B, A, and this is XZ. There's no cycle in this. We did not complete a cycle. The X is the A, and the Z is the ABA. So getting to the cycle, we completed 0 instances of the cycle, and we got from the end of the cycle to the final state. If we repeated that cycle, if we did that cycle once, the string that we would generate is A, B, B, A, B, A. And now again, we have X as the A. The next 3 characters, ABB is our Y, and then the ABA is our Z. So we're breaking this down into getting to the cycle, iterating the cycle, and then getting from the end of the cycle to a final state. Do we agree that as long as we have this breakdown, we can repeat this cycle an arbitrary number of times? We can do this ABB, 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 and it doesn't change Z what it takes to get from the end of the cycle to the final state. So that's what's getting pumped, is this concept of this cycle. But the important part is that this cycle has to happen within the first M characters. And by making this string, instead of having some A's and some B's, the conclusion that we've drawn is this is a legal string in WWR. If there's a finite number of states in this DFA, M, then it needs to be able to accept this string within those M states. But the first M characters of this string are all A's, which means that we need to have read all A's by the time we complete a cycle. It doesn't mean that every edge in the DFA is an A. It could be that this is also a B. It could be that this is also a B. And maybe this is a B. This starts to make a little bit more sense, like maybe we could do some kind of WWR, where we read some A's, and then we get to this point, we read some B's to finish us off. Maybe that makes a little bit more sense. And again, this isn't a total DFA, more like an NFA for just illustration purposes. But at this point, assuming that we could accept something like A, B, B, there's no way to make it work. But imagining that it did work somehow on this path, there's no way that by iterating this cycle an extra time, assuming that we had a way to read all A's, this would be saying, because this cycle is of length 3, we can add 3 more A's to this by just repeating Y one more time. And those 3 extra A's would appear here. If we look at just XC, that path from initial state to final state, this XYZ somehow was A to the M, B to the M, B to the M, A to the M. But we know that the Y happened in all A's right here. When we add an extra cycle to that, we're adding extra A's to this. So we're increasing the number of A's. That's an arrow, not a squiggly. We're increasing the number of A's at this point in the string, and we're not increasing them here because this was part of Z. This was part of getting from the end of a cycle to a final state. So we've broken this down into 3 components. 1 component can be iterated. 2 components are set in stone, getting to the cycle and getting from the end of the cycle to the final state. We can pump this. It has to be in that portion of the string. Because it is in that portion of the string, we can choose a number of repetitions of this loop such that the end result, which would be accepted by this DFA, is not in the language. Which is the important conclusion. Did that help, or did that confuse things further? It's quite complicated. All right, any questions before I erase things? How can I make this clearer, make more sense? What are the questions you have? What are the clarifications, or just that this part makes no sense to me? This whole thing makes no sense to me. Yeah.
I kind of have one, but isn't this right here, when we do this, we have to prove that it doesn't work for any DFA.
Right.
But isn't this only proving it that it doesn't work for this specific DFA?
When we instantiate M, yes. So I'm drawing it out like it has 5 states, but when we're talking about M in general here, when we say that we're creating a string with M, 4 M characters, of which the first M are all A's, that's how that works. So basically, any number that player 1 could pick for this becomes M, and our entire argument is based on M. When I draw out a 5-state DFA, it's for illustration purposes. And yes, if I said the string is 5 A's followed by 5 B's followed by 5 B's followed by 5 A's, suddenly it doesn't work at all. That just proves that it doesn't work for a 5-state DFA. But if player 1 said 6, then you can imagine there being a 6-state DFA. And our string is 6 A's, 6 B's, 6 B's, 6 A's. Then the cycle is closed within the first 6 characters, all of which must be A's. The argument continues to work for whatever we instantiate M as. But how you will disseminate this in writing, you will never instantiate the M. You will always leave it as the string is A to the M, B to the M, B to the M, A to the M. The cycle must be closed within the first M characters. X, Y must come from all A's. And because of this, when we pump Y 2 times, we have an unequal number of A's as A's here at the end. Therefore, this string pumped twice cannot be in the language WWR, therefore this DFA can't exist. Basically, something like that. Anything else I can answer? Probably help to see an additional example. All right. AB alphabet, language strings with more B's than A's. How could we show that this language is not regular? This says nothing about the order of the A's and B's. But remember that you get to pick the string as player 2. So you can make restrictions to this language as long as that restriction adheres to the language. So you could force an order to this. So the first thing that you should think about when you're doing this is, what is the string? So from player 1's perspective, they've picked M, but your argument has to show that it's impossible for player 1 to win the game. So you need to pick a string that's based on M. incorporates M, that number of states in the DFA, somehow. What is a good string for this? It's especially good if you can pick a string that's close to something that we've talked about or we've seen before. What are the languages that we have seen so far that are not regular? We've seen a couple of them. One in the last example, and one that we talked about a little bit before that. What were those languages? One on the last slide was WWR. What was the one before that?
It was. A to the N.
A to the N, B to the N. That one's nice and simple. Is there an easy modification we could make to A to the N, B to the N, such that we force that there are more B's than A's?
You can add another.
Yeah, that's exactly a good choice. A to the N, B to the M plus 1 is a language that is extremely close to a language we already know is not regular. So any DFA that works for the language of strings with more B's than A's needs to work for this string. Take what we know so far and see if we can craft an argument, a logical argument for why this language can't be regular. What do we know about the portion of the string that is XY? Definitely starts with an A. Anything more we know than that?
It'll. Yeah. Whoops, sorry.
It will, yeah, there's a cycle somewhere. Since there are more than M characters in this string, this DFA has to have a cycle in it somewhere, since M is the number of states in the accepting DFA. Where is that cycle guaranteed to be? In all A's. Why?
It's the same for our states.
Yeah. Yeah, we have to have closed that cycle by the time we reach the end of the A's. By the properties of a DFA. Which means that we can pump extra A's into this string.
We just pump once just to add the same number of A's.
Yeah, in order for there to be more B's than A's, even as soon as we add a single A to this, that property is no longer true. Note that we could have picked A to the M, B to the M plus 2, or A to the M, B to the 2M, or A to the M, B to the M factorial. We could have chosen a bunch of arbitrary strings here where this is true. But just like in programming, it's very good to pick something that's right on the decision boundary, right on that edge between accepting and not accepting, because it will place the fewest restrictions on your proof. As soon as you pick 2M, we need to show that we can pump enough A's into this to double the number of A's. And that just adds an unnecessary complication to this. If we pick A to the M, B to the M plus 1, we only need one extra A in order to break this language. Come up with an example of something that's not in this language. Yeah.
What instead we did B to the N plus 1 and then A. Will we still do the same idea with pump A
you would actually, everything would be forced to be in the B's at that point, and the only recourse. It would only work for B to the M plus one, A to the M. As soon as you had more B's than that, it wouldn't work. You would actually pump down. You would set I to 0 at that point.
It would be the same amount of fees.
Yeah. Or fewer. But that would be the only way to do it. So we want the A's first so that we can pump up, because we can only pump down once. If you take the string XZ, that's you're iterating that loop 0 times. And XYZ, the string that we're saying is A to the M, B to the M plus 1, that is XYZ. We're iterating that cycle once when we make this string. So we can only remove one loop, and we can add an arbitrary number of them. All right, so we know that both X, Y, and Y are restricted to be all A's. We know that to be true. Does that make intuitive sense to people as to why that is?
So technically, could it be that it never even reaches B?
Yeah. It could be that there is a way to accept something that is all A's. That wouldn't fit the language.
Well, sorry, what I mean is just that the idea here is that it's indefinite, and that's why it's wrong.
Yeah, well, Z, this part that goes from the cycle to the end of the string, is what has to eat all the B's in this. So assuming that this DFA does exist, then we can recognize A to the M, B to the M plus 1. And that path, since the cycle has to be completed within the A's, all of those M plus 1 B's have to be eaten, have to be consumed from the path from the end of that cycle to the final state. There may be other cycles in there that consume those B's, but we're saying that there exists a path from starting state to final state that reads A to the M, B to the M plus 1. So it doesn't matter if there are other cycles, there just is a cycle that consumes A's. And since there's a path through that cycle once that gets to that final state reading that string, we'll just iterate that cycle one more time and take exactly the path that we did before that accepted A to the M, B to the M plus 1. And that creates a path through this DFA for a string that this language can't accept. Which is a bit challenging to see. So one way to think about this, I still like to break it down into the 3-state problem because I feel like that's as simple as it is to see, but recognizing that there could be more than these 3 states, but we break down the path into getting to iterating and getting to the final state. That's as simple as we can make it with an initial state and some final state. This can be an arbitrary number of states now, the way that I'm seeing this. X can be consumed by going through 10 states or 15 states. This cycle can be seen as doing something. But the idea is that X consists of all A's and Y consists of all A's. Z consists of potentially some A's, but definitely all of the B's. So whatever path this Z took, we're going to hold that constant. Whatever path this X took, we're going to hold that constant. But X, Y, Z creates A to the M, B to the M plus 1. Somehow. There could be extra cycles in Z. There could be extra cycles in X. We don't really care. We just know that there is a cycle that happens within the first M characters, which are all A's. So the cycle is all A's. And this path here was all A's. So we iterate this cycle one more time. We're producing at least one more A. Holding this path, XZ constant, which we know was already a path from initial state to final state. Since this path accepted this string, iterating this loop one more time creates a string, not in the language, which cannot exist if this DFA perfectly recognizes the language of strings with more B's than A's. If it accepts this, then there needs to be a path that accepts this. Hold this path constant. Find that cycle within the first M characters, repeat it one extra time. We've found an accepting string that's not in the language, meaning this DFA can't have existed in the first place. How are we doing? I get some Complete and total lack of feedback, which is great. Some thumbs up, some blank stares. What do the blank stares mean? I don't want to just be that professor who lectures at you, says see, and then moves on. I want there to be a little bit of back and forth, especially if there's something that I can do to help. I've been in that class too, where the professor is just writes all over the board, something that no one in the class understands, just kind of points at it, like, you get it, right? And then erases it and moves on. I've been that student too.
Well, basically, the idea is that we don't really care how the DFA looks. We just want to prove it.
Yeah, it's in the abstract because it doesn't exist. It can't exist. But we're going to assume that it does exist. And if it does exist, then it must hold certain properties. And we can show that if it did exist and those properties did hold, then we could produce something not in the language. Since it could produce something not in the language, then that DFA can't have existed in the first place because it accepted something that wasn't in the language. So that's exactly why it's a proof by contradiction. Because we assume it exists and then we derive the contradiction. If it existed, then it would have to accept a string that's not in the language. By any definition that it could exist. But it all hinges on this picking of a good string. If you don't pick a good string here, it actually may be completely impossible to show this. It's not something that will always work. It's just something that can work if you pick a good string. So moving forward from this, we see that we pump y, the resulting string is not necessarily in the language. In fact, it can't be in the language. We have a to the m, b to the m plus 1. We've pumped y consisting of all a's at least once. That adds at least one a. Whatever the length of y is, it adds that many a's to the string. So the resulting string that we can show is accepted via x, y, y, z is a to the m plus the length of y, b to the m plus 1. And since we know the length of y is at least 1, then the number of a's have to be greater than or equal to the number of b's, by definition. And if the a's are greater than or equal to the number of b's, then it's not a string with more b's than a's. All right, let's get another example. Let's see if we can come up with the intuition for another example. Show that the language AB to the N, A to the K, such that N is greater than K and K is greater than or equal to 0, is not regular. The question I have for you, what is a good choice for the string W? This one's a bit harder.
ABA.
So we need M in there somewhere, but I like the idea of, so that does adhere to the language. In that case, N is 2 and K is 1.
Yeah.
So that would work. Can we phrase that in terms of M somehow? So we know basically we need an N and we need a K. So we need AB. Be nice to put this in terms of M something. It needs to be strictly greater than K.
M+1.
We could try M+1, something that's right on that boundary. What is a good superscript for A then?
M.
M? Let's roll with this. This seems like a good idea. In fact, the exact idea I have here. Why is this a good string? First of all, what do we know about the breakdown of X and Y? It's somewhere in this set of ABs. In fact, it's somewhere in the first half of this set of ABs. Let's draw out a few ABs. And take a look at some cases. So assuming this goes on long enough for X and Y to be somewhere in here, we know it starts with an A, which means that we know X starts with an A. But what are the options for Y? It breaks down into 4 cases. What are the 4 cases for how Y could look? It could start with an A, end with an A. It could start with an A, end with a B. It could start with a B, end with a B. Or it could start with a B, end with an A, I guess.
Shouldn't that be 5 then, since Y, the length of Y can be 0?
Length of Y has to be at least 1. We have to have some cycle somewhere in those first M characters. So that cycle either starts with an A, ends with an A, starts with an A, ends with a B, starts with a B, ends with an A, or starts with a B, ends with a B. All we know about X is it starts with an A, but it turns out really not to matter. Because as soon as we start repeating some of these Ys, some of them are going to break the style of the language, and some of them are going to continue to be pumped in a way that will break this N is greater than K, or a way for us to remove some such that we break that. So the removing is going to be what ends up happening here. But let's first identify those cases for which it's an obvious breaking of this language. Which are those cases? If you were to repeat Y, what result of that is obviously no longer in that language?
Starts with the B, ends. Oh. But are the letters in between, like, we have B, A, B, A, but the only thing we know is it starts with B and ends with A.
Right.
We don't know.
We don't know exactly how long it is,
Yeah.
but we know it's at least 1. So if we're saying that it starts with an A, ends with a B, it has to be at least 2 characters. Can't be 1, can't be 3. Has to be even, has to be at least 2. So remember that, yeah, the length of Y has to be greater than or equal to 1. We have to have a cycle, is what that says.
So starts with an A, ends with an E would be valid.
It would be valid, because if you repeat that, what comes afterwards are some more ABs. But if we have starts with an A, ends with an A, what happens when we repeat that? So you can imagine that we take this Y here and we repeat it. So we just take X as a constant. Then we take Y, A, B, A. We repeat Y again, A, B, A. And then we continue B, etc. we've produced two A's in a row right there in a way that is not AB to the n. And this occurred somewhere in that AB to the m plus 1. There's no way for this to be on the boundary of this because there are two m characters, 2m plus 2 characters within here. So this boundary has to be within the AB to the m portion of this string. And this breaks the way of this language. The string is no longer in this language because of those repeat days. The same thing is the case for anything that repeats b's, starts with a b, ends with a b. So this case is easy to show by setting I equal to 2. We pump the string one extra time, and we get a portion of this string that does not adhere to that structure. Same with this case. Starts with a b, ends with a b. Duplicate it, you're going to have 2 consecutive b's at the point of duplication. That can't happen within that string, within that language. What remains are the 2 other cases. How could we possibly show that these other cases, there's some other way to not make this work?
But do we need to? We've already proven it wrong.
We do.
Oh.
Because this says that there is such a breakdown, and player 1 is responsible for the breakdown of XYZ. So player 1 could pick something like this, and you would have to be able to show. Basically, this ends up, if we want to use predicate logic, what is it? It's for all possible m, there exists a string W, such that for all possible breakdowns of XYZ, there exists a counterexample. So in predicate logic, you're trying to show a for all, there exists, for all, there exists something. So your proof has to adhere to a long predicate chain of logic. That's why we take the role of player 2. We just have to prove the there exists. So we pick the string, but we have to say a string that works for every possible breakdown. When we pick the amount to pump, the I, it has to be for all possible breakdowns of XY. XYZ. Tying that back to history, hopefully in ways that you've seen before. Any thoughts or ideas? When we have this AB, if we run through the loop more times, what we're doing is we're increasing the value of n here, which increases this value of m plus 1. And it still adheres to that form. We're duplicating extra ABs. This is not helpful. N is still greater than k, and k is still greater than or equal to 0. This did not do anything helpful or useful. However, remember that this, AB to the m plus 1, a to the m, is XYZ. There is a path to acceptance if we take out the y. So what we know about this y is it has to be at least one character. And to start with an a and end with a b, the only way to do that is to have 2 or more characters, which is a single repetition of this AB. So if we remove y, at least one AB from this, then we're taking this down at least one time. If you're removing a single AB, then we go from AB to the m plus 1 to AB to the m. And that violates the n is greater than k property of the language. So the correct path through this for these two is to say, for here we set I equal to 2. And here we set I equal to 2. That said, just run through the loop one extra time. We have x, y to the I, z as the pump. So that's what that I stands for, is the number of times that we run through that loop. So we're saying set this to 2 and now we run through the loop twice instead of once. And when we do that, we break the AB to the n portion of the string. When we set I to 0 for these two cases, we're saying remove the loop. Go straight from x, no y, straight to z. And that's going to remove at least one AB from this, bumping down this m plus 1 at least one time, and that breaks the n is strictly greater than k. And that would not have worked if we hadn't picked something that was immediately next to this, the m plus 1 and the m here. If we said m plus 2, suddenly proof invalid. If we pick 2m, proof invalid, because we don't know the length of y. It has to be able to work for exactly 2 characters. And there's no guarantee if we pick something like AB to the 2m, a to the m, then what we would have shown is that we end up with, through this whole process, AB to the 2m minus the length of y, which has to be even. So this would be as low as 2, a to the m. And there's no guarantee that 2m minus 2 is less than m. It's still very possible that it could be greater than and still adhere to the language. So you have to pick something that is guaranteed to break that condition. And in this case, it's close enough that by bumping this down by 2, bumping the 1 here down to m, you have to have broken that condition. And that's because we chose something that was right on that decision boundary. How are we doing with that? Did it make sense to break these down into those 4 cases? Did those 4 cases seem exhaustive? There's no other way that we could represent y within the scope of somewhere in the first m characters. Does that part make sense? So we have our 4 cases. We need to then show for each of those 4 cases. If we have an odd length y, then it must start and end with the same character. By pumping that an extra time, we break. And if it is even length, it has to be at least 2 due to this condition. So we're removing at least one of these AB pairs when we set I to 0, which breaks the n is greater than k. And since we now have a counterexample for every single case, if player 1 chooses some breakdown that matches, you just have to match the case that they pick. They say X, Y, Z is this particular breakdown. You figure out which one of these cases that breakdown adheres to, and then you use this algorithm to come up with the counterexample. That says that the DFA that you say exists with this particular breakdown, here is the counter that accepts a string that's not in the language. And this shows that no such DFA could have existed in the first place, of any size. You don't have to go through any exhaustive work of proving that no DFA of size 2 exists, size 3 exists, size 4 exists. That process would never terminate. You'd never have a proof if you did this exhaustively. But since we have something that works in the abstract, regardless of what m is, then we do in fact have a proof that no such DFA could exist. What can I answer? I don't want to dive into the next thing with just a couple minutes to go, a minute to go. What can I answer? How can I help? How can I make this clearer?
So would the 2m, a, b to the 2m been a valid solution or valid?
No,
No,
we could not have picked this because when it would work for the I equals 2 cases here, but for the I equals 0 case, when we pump it down, there's no guarantee that 2m minus the smallest possible length of y that we could have is less than this m,
Yep.
less than or equal to this m. So it's very possible that this still adheres to that. And there's just no way for us to construct that proof. So in that case, player one would have won the game. We were playing it as a one shot. Just because we picked the wrong string on our very first turn. So the hardest part of these proofs, once you understand kind of this breakdown and process, I think is picking a good string. You pick a bad string, the entire proof is impossible. You have to pick a good string. That's how the rest of the proof works. All right, I have office hours starting now. I anticipate I'll be seeing a good few of you. Remember that I also have availability from about 12 to 1. So if you have any questions, would like to work in my office, as a few of you have discovered is a fun place to be. I don't know about fun, but it's a productive place to be. I'll see you soon.